All right, everyone. It's 11:30, so maybe we can look at the solutions to the problems in the workshop. Um, yeah, so the first two questions involve rearranging. Let's do the first rearranging. You're given delta x equals vi times delta t plus 1/2 a delta t squared, and you want to work out what is vi. Right. So let's start building this equation up. Vi is tied up with delta t via multiplication, and then it's added to 1/2 a delta t squared. So first we multiply vi with delta t. Okay. Then we have vi delta t, and then we add 1/2 a delta t squared, and that builds the equation up, vi delta t plus 1/2 a delta t squared, and that's equal to delta x. Okay, let's now go back and undo the operations that we did. So we'll start with delta x, and the last operation we did was to add 1/2 a delta t squared, so we need to subtract 1/2 a delta t squared from delta x, doing the inverse operation. So that will be delta x minus 1/2 a delta t squared. Then we undo the times delta t. Reverse of times is divide, so divided by delta t. We then have delta x minus 1/2 a delta t squared, divide that by delta t. And then we're back to vi. Therefore, vi is equal to delta x minus 1/2 a delta t squared divided by delta t. All right. Okay, so if you have any question, feel free to pop it in the chat box. Or if anything is unclear and you need more clarification, please let me know as well. You can also unmute yourself and speak directly, of course, if that's what you prefer. So for the second question, I think we already rearranged this in class, so we won't do this again. Delta x, we found that to be vf squared minus vi squared over 2a. Right, now for this worded problem, so 54 kilometers per hour, when we're solving for problems, especially using kinematic equations or any equations, our units need to be consistent, preferably in SI units or standard units. So 54 kilometers per hour, that is equal to 15 meters per second. So distances in meters and times in seconds. Right. So we'll use 15 meters per second. So the scenario here is that you're driving you're driving along the road at a speed of 15 meters per second, right? And then 15 meters away, a ball appeared out of nowhere behind the parked cars. So that's 15 meters away. You slammed on the brakes, but you didn't slam on the brakes immediately. You had 0.7 seconds of reaction time. So you only slowed down after 0.75 seconds. So that means that you would have traveled a certain distance, delta x, before you slammed on the brake. So delta x, let's say this is the distance, and you're just moving on a straight line, so that distance is equal to displacement. Distance traveled by the time you hit the brakes after 0.75 seconds. So there are two aspects in this problem here. The distance that you trust, so you're moving, and then you saw the ball, you're still moving a certain distance before you hit the brakes. Once you hit the brakes after 0.75 seconds, you slow down. But while slowing down, you are traveling, you traveled a certain distance as well. So there are two distances involved here. The distance before you slammed the brakes and the distance that you traveled while you are decelerating after you've slammed the brakes. Okay, so first let's solve yeah, so there are two distances. So that's the first distance there. And the second distance will be the distance that you traveled, delta x2, distance while decelerating. And we sort of have to figure out whether the combined distance that you traveled would be more than 15 meters, in which case you would have hit the ball, or will it be less than 15 meters, in which case the ball would be safe. And if there's a child, the child would also be safe. Right, so let's figure out the first distance. Distance traveled by the time you hit the brakes after 0.75 seconds. So you're given the speed, 15 meters per second, and the time, which is 0.75 seconds, because that's your reaction time. Okay, yeah, before you slam the brakes, how far did you travel? You only have speed and time, but you know the definition of speed is equal to distance over time, right? From the definition of speed, speed is equal to distance over time. So from here, we can figure out what is the distance d. Yeah, delta x would also be equal to distance in this case, because you're moving along a straight line. Displacement delta x is equal to distance. Right, so to figure out d, we have to rearrange this equation here to isolate d. Right, you can do the method that we did, so building up the equation and then doing the reverse one. So say starting with d, you have to divide that with t, so that you have d divided by t, and that will give you the speed s. And then going backwards, you start with s, multiply that with t, so you have speed times time, which will give you distance. So distance is equal to speed times the time. So you can do that method that we learned for rearranging. But also, if you only have three variables that are, especially in this arrangement, s is equal to d over t, you can also use the mathematical rule that any number divided by itself is equal to 1. So, and whatever you do on one side of the equation, you have to do on the other side. You have to do on the other side. So that if I multiply both sides with t, so if I multiply the right side with t, I have to multiply the left side with t as well, so that I'm not changing the equation. And the reason why I multiply with t is because any number divided by itself is equal to 1. So that t divided by t is equal to 1. and I have just D on the other side, and you have T times S on the left side, which is the same rearranging that we did using the method of building up and tearing down. Yeah. So yeah, as I've said, it's up to you if you're used to doing this method here, the second method that I did, you can use that, or you can also use the method we just learned with building up and tearing down. You'll have the same rearranged equation. But then we can now solve for the distance. I just need more space here. Yeah, put more space. So we can now figure out how far you traveled before you slammed the brakes, so that your speed is 15 meters per second and the time is 0.75 seconds. So you would have traveled about 11.25 meters, or rounding that to two significant figures would be 11 meters. Right, so you would have traveled 11 meters before you slammed on the brakes. Okay, so then you start to decelerate, and we need now to figure out how far you would travel until you stop. And for the second part of the motion, need more space here. Now, while decelerating, how far would you have traveled? Okay, now it involves deceleration or negative acceleration. That sort of gives us a clue that kinematic equations is sort of involved, because you want to find the distance delta x, you want to, and then you have acceleration, and then you have final velocity and initial velocity. So that sort of gives you a clue that you need kinematic equations. So you fill out your table of facts. Okay, delta x, that's what we want to find, how far we traveled. Your initial velocity, 15 meters per second, and you slam the brakes until you stop. So your final velocity will be 0. And you are decelerating at 6.5 meters per second squared. So remember to include the negative sign in your acceleration, because deceleration means slowing down. Okay. The time it takes you to slow down to a complete stop is not given. So we don't know delta t. We only know VI, VF, and A, and we need to figure out delta x. Okay. So you look at your kinematic equations here, right? Kinematic equations, let's say kinematic equation 1, 2, 3, 4, and 5. You don't know delta t, so anything that involves delta t is useless for solving the problem, right? And you're only left with this vf squared equals vi squared plus 2a delta x. And we already rearranged this to isolate delta x, so we can use that right away. Yeah, we already rearranged that equation so that delta x is equal to vf squared minus vi squared over 2a. Right, so then you can solve delta x, your stopping, so that's 0 for your vf, minus vi is 15 squared, so don't forget there's a square, divided by 2 times negative 6.5. So remember to include the negative sign in your calculation. Right, plugging everything in the calculator. Again, you might need to put a bracket in the denominator. So it's 15 squared divided by the whole bracket 2 times negative 6.5. And you should get a delta x of about 17.3 meters, rounded that to two significant figures of 17 meters. Right, so that means in the process of decelerating and stopping, okay, you would have traveled 17 meters. Okay, and so the total distance that you needed to stop completely would be 11 meters plus 17 meters, which is 28 meters. By the time you've stopped, it's farther than where the ball is. So in that case, you would have hit the ball, and if there was a child there, you probably also would have hit the child, unfortunately. Right, and it seems like even if you had zero reaction time, the time it takes you to decelerate to 0 meters per second, you would have traveled still 17 meters. It's still farther than where the ball is. So yeah, so you would have hit the ball as well, even if you had zero reaction time. All right, any question about the solution to that problem? Or are we, does that make sense? And are we okay with that solution? Yeah, all right, good. Okay, thank you for the thumbs up. Then we can proceed to the next question. Right, you're driving to the campus, which is 8.5 kilometers away. So 8.5 kilometers, that's 8,500 meters. There are 8 traffic lights. Usually you have to stop at 6 red lights, and every time you stop, you spend 30 seconds waiting for the red light to turn green again. Okay, and you're late to class, so you drive faster at 65 kilometers per hour. 65 kilometers per hour converted to meters per second would be about 18 meters per second. Okay, usually, if you're not in a hurry, you're driving at 50 kilometers per hour, which is about 14 meters per second. Okay, so how much time do you gain by speeding up? So the question here is, how long will it take you to travel if you're traveling? How long will it take you to travel 8,500 meters if you're going at 18 meters per second? And compare that to how long it will take you to travel 8,500 meters if you're going at a speed of 14 meters per second. So, so how much time? That means we need to figure out the time interval, delta t. We are given the speed. We're given the speed is equal to 18 meters per second or 14 meters per second, depending on whether you're speeding up or slowing down. And we're given the distance, which is 8,500 meters. Okay. So reading this question, there's no information about acceleration. So you can sort of assume that it's the definition for speed that you need instead of the kinematic equations. So from definition, speed is equal to distance over time. Okay, and we need to figure out the time. So we're assuming that t initial is equal to 0. That's when you start traveling. So delta t will just be, we can just write delta t as t for simplicity. And we're just looking for the time it takes you to travel, the distance of 8,500 meters. Now we have to rearrange this equation. to isolate time. The tricky bit here is that time is in the denominator, so it's below the division bar. It's easier if the time is above the division bar. So what we can do to, before we do any rearranging in this equation, is to flip the equation. You can do anything to your equation as long as you do it to both sides of the equal sign. Then you're not changing the equation, and whatever you do is valid. So if you flip the equation, we need to flip both sides. So if you flip the right hand side, so that's t divided by d, we also need to flip the left hand side. Once if you see just s by itself, it's implied that s divided by 1, because anything that you divide by 1 is equal to that same thing. That's why we don't explicitly put divided by 1, but if you see just a single s there, it implies that it's s divided by 1, so that if you flip s divided by 1, that will be 1 over s. Okay, right. So it's a sort of a mathematical rule. So for example, you find 14. Okay, implicitly that's 14 over 1, but we don't put divided by 1 because we know that any number divided by 1 is itself. So 14 is the same as 14 divided by 1, so that if you flip this, it's 1 over 14. It's the same concept here. Let me just erase this. It's the same concept. Why, if we flip s, it's 1 over s, because s is implicitly divided by 1. All right, does that make sense? I hope that's not confusing. Right, so then we can rearrange this equation to find t. We can multiply both sides with d, so that any number divided by itself is equal to 1. And we can do d divided by d is equal to 1. And we only have t on the right hand side, and you have d over s on the left hand side. So time is equal to distance over speed. Okay, are we okay with that? Yeah, you can also do the building up and tearing down after you flip the equation. So after you flip the equation, that's 1 over s is equal to t over d. You build the equation starting from what you want to isolate, t. You divide that by d, you have t over d, and that gives you 1 over s. And going back, you have 1 over s, undo the division by multiplying with d. You have d over s, which is t. So it's the same thing. T is equal to d over s. So you can use any method for rearranging that equation there. You just need more space here. Right, so we have the expression for time. We can now solve the time. For the speed is equal to 18 meters per second. The time is equal to the distance, 8,500 meters, divided by the speed, which is 18, will give you a time of 472 seconds. And when your speed is equal to 14 meters per second, when you're not in a hurry, the time is equal to the distance that you travel, 8,500 meters divided by your speed. And that will give you a time of 607 seconds. And let me just put some more space. I need some more space here. do like this. Oh, okay, let me write this down here. So your time when you're going at 14 meters per second is 607 seconds. Okay, so so what's the time difference? How much time do you gain by speeding? By comparing this to, this is the time when you're speeding, and this is the time when you're driving at your regular speed. So we can subtract these two. The difference in time will be 607 minus 472 will give you a difference in time of around 135 seconds. So this is how much time you will gain by speeding up. The time that you wait in front of the stoplight, for it to turn green, it's the same regardless of whether you're speeding up or you're driving at your normal pace. So that equals each other out. So it's just 135 seconds as the time difference. All right. Okay, and what are your average speeds in both cases? So you might be thinking you're given the speeds already, 65 kilometers per hour or 18 meters per second, and 50 kilometers per hour or 14 meters per second. But that's just your driving time. It does not include the time you spend waiting for the red light to turn green. So the question being asked in B, your average speed, should include the time that that it takes for you to wait for the red light to turn green. So for the average speed, that's distance over time, but this time should include the driving time plus the waiting time. Right? The waiting time, the problem says you spend, right? So the problem says you spend an average of 30 seconds in front of each red light, but there are 8 traffic lights, but you only stop at 6 red lights. So you're only waiting for 30 seconds at 6 red lights. So the total time that you're waiting will be 30 seconds times the 6 red lights that you have to wait for. So that will be 6 red lights times you're spending 30 seconds at each red light. So that will be a waiting time of 180 seconds. Right? So your average speed for when you're driving at 65 kilometers per hour or 18 meters per second. 18 meters, we can stop to work. Okay, my pen. 18 meters per second. Right, your average speed will be the distance 8,500 meters divided by your driving time. We've solved that here. When you're going at 18 meters per second, your driving time is 472 seconds, plus the waiting time is 180 seconds. So that will give you an average speeds of, yeah, so remember to put brackets when you're putting it in your calculator, put brackets for the total time. That will give you a speed of 13.04 meters per second, or that's about 13 meters per second rounded to two significant figures. And when your speed is 50 kilometers per hour or 14 meters per second, your average speed will be the distance that you travel, 8,500, divided by your driving time. We've solved that earlier, 607 seconds plus the waiting time, 180 seconds, and I need more space. So, oh, okay, I'll just write it here. Right, so that will be an average speed of about 10.8 meters per second, or that's about 11 meters per second, rounded to two significant figures. So you'd still, yeah, even, yeah, or finally, it makes sense that even if you're considering the waiting time, okay, your average driving speed should still be smaller if your driving time is slower as well. All right. Any question about the solutions for the workshop problems, or any question about the lecture, the topic we've covered today so far? Right. Or any question about the lab or anything else? I don't see any questions in the chat box. Okay. Just one quick announcement. I don't know if you received the email I sent yesterday about the review workshops this afternoon. So it's supposed to be face to face, but unfortunately, I have to isolate, so I won't be able to do the face to face workshop. And so I'm moving that to an online review workshop, but it will be like a drop-in session for anyone. If you have any questions, or if you want to go over something else, something to be explained again, or if you want to go through a problem again, or anything you want to ask about the labs or the topics that we've covered so far, then please come to the drop-in session. The Zoom link is the same as the Zoom link for our lectures and workshops, and it's on stream, right? So yeah, so if there are no questions, so I don't see any questions in the chat box still. Yeah, then I will be online from 1 o'clock for the drop-in sessions, and hopefully see you there. Okay, good. Otherwise, have a good weekend, everyone, and I'll see you next week.